Alright, my name is Shawn Anand, and my project is the use of rational drug design to synthesize novel PARP1 inhibitors for cancer treatment. Rational drug design is a process of creating organic compounds to specifically target biomolecules. According to the World Health Organization, cancer lies in one of the top 10 causes of death worldwide, and even though cancer treatment has increased in the past 10 years, there is still a need for treatment that can specifically target the cancer cells and leave normal cells unharmed. For the past 2 summers, I've been lucky enough to work in a lab involved in cancer treatment via the PARP1 enzyme. PARP1 is an enzyme involved in DNA repair. However, it is a special use in cancer cells. The reason for this is that because of the uncontrolled replication in cancer cells, other repair enzymes such as BRCA1 and BRCA2 cannot function, and therefore PARP1 is the only thing for the cancer cells to fall back on when in need of repair. So therefore, by inhibiting PARP1, cancer cells will not be able to repair themselves, whereas normal cells will have other enzymes, like I said before, such as BRCA1 and BRCA2. So, like any other enzyme, PARP1 consumes a substrate. The substrate it consumes is known as NAD, or nicotinamide adenosine dinucleotide, and you can see the structure of that compound in my logbook here. So I hypothesized that to inhibit PARP1, to create a successful competitive inhibitor, I would have to model my compound after the structure of NAD. And the compound I chose is this amide compound, as you can see here. And its structure is similar to NAD in that it contains a fused benzyl ring here, a pyrimidine ring, and the carboxamide group. So last year, the compound I created solely focused on one part of the structure of NAD, which was a carboxamide group. And by solely focusing on this part, this compound was not active when trying to inhibit PARP1. So to create this final amide compound, first I needed a two-step reaction. The first step can be seen here, which involves a conversion of this acid to amino-nicotinic acid to this acid, which is the acid form of the final carboxamide. Because as you can see, the structure is identical. However, instead of the carboxamide group, there is a carboxylic acid group, which is the COOH group. So for the first conversion, the mechanism of this reaction can be seen here. And to summarize it, the main processes that occur is that the electron-deficient carbon that is a part of the carbonyl group, which is a carbon that is double bonded to an L, causes other compounds with that have many electrons, such as lone pairs, to attack at that spot to increase stability by achieving a formal charge of 0. So these are the processes that occur during this whole conversion here, the first conversion. A similar process happens in the second conversion during the mechanism. However, a difference is that instead of solely attacking the carbon that has a deficiency in electrons, they're also focusing on the oxygen to create a formal charge of 0, and therefore create stability within the compound. So after I synthesized these compounds, before I could confirm the identity, first I had to purify them to get rid of extraneous chemicals. So one example of a purification technique I use is known as column chromatography, and this involves the use of a column of silica, which is silicon dioxide, a polar compound. So what I did was I ran my solution down the silica, and polar impurities will react with the silica, and therefore will remain higher up in the tube, whereas the nonpolar compound will go down much more quickly and can be collected separately. And for this contraption, you can see it here in my logbook as well. So after I used various purification techniques, I could finally confirm the identities of my compound. And I confirmed the identities of my compound using a process called proton NMR. And what this does is this maps out the structure of the compound by using the protons in the compound and their various magnetic spins when exposed to an electric field. So these two proton These two proton NMR spectra are for the respective compounds here. This one is for the carboxylic acid. This is for the carboxamide group right here. So for the first carboxylic acid, in total there are 7 protons. There are 3 from the pyrimidine ring, 3 from the fused benzyl ring, and then 1 from the carboxylic acid group. So as you can see here, from the carboxylic acid group, the singlet can be seen at the ppm of 6.45. And from the pyrimidine ring, there is 1 triplet and 2 doublets. The triplet can be seen at 7.6, and the 2 doublets can be seen at 8.7 and 9.2 respectively, as you can see here. And the 3 singlets from the methyl group can be seen at the ppms of 6.45, which can be seen in the spectra here. Now for the second spectrum, it is simply the carboxamide form of this carboxylic acid group. So therefore, there is solely 1 more proton because the carboxylic acid is COOH and the carboxamide is a double bonded O to an NH2. So there's simply 1 more proton and 1 more singlet, which can be seen here at the ppm of 9.1. So I successfully created these compounds and confirmed the identities. When I sent the final compound for testing in a biological laboratory against a PARP1 enzyme, it demonstrated 43% inhibition against the enzyme at 5 micromolar. And this percent is very close to the lab standard of a high 40%, which is used to determine if this compound will be used in further experimentation, such as larger scale, such as in mice. So in conclusion, I successfully synthesized both of these compounds, and the final compound, which I thought would be an active inhibitor against PARP1, was indeed very close to doing so. And for further experimentation, I'll be doing small modifications to the compound to finally get it over the hurdle and allow for further experimentation. A possible compound that I will synthesize next can be seen here, and this involves the substitution of the methyl group for an iodine group because the high electronegativity of iodine has shown affinity for the PARP1 active site, and therefore may increase its affinity and the percent inhibition overall. So this project demonstrates the use of rational drug design in cancer treatment, and hopefully in the future I'll create a compound that will be active against PARP1 and will become a part of the market after further experimentation. Thank you for listening to my presentation. Peace.